Yeah. Let me give you a definition. And the definition is that of a group homomorphism. So say let A and B, say, be two groups. I'm not using G, as you can see. Now, if, say, F is a map from A to B, such that, say, for A1, for any A1 and A2 in the group A, one gets, say, B1 is F of A1 and B2 is F of A2, such that we actually didn't need to use B1 and B2, but let me just use them anyway. F of A1, F of A2 is equal to F of A1, A2, where this multiplication is the multiplication in the second group B, and this multiplication is the multiplication is in the first group. Of course, this we can write as, say, B1, B2 is equal to F of A1, A2. Actually, I don't, sorry, I got a little confused. Let me just clean up the notation, right? Let me just not use. Okay, let me start again. So let's talk about group homomorphism. So let A and B be two groups such that if F is the map from A to B, such that for any A1 and A2 in the first group, one gets under the map, say, F of A1 times F of A2. This multiplication will be in the second group, right? So let's give it a subscript B. So that is equal to, if you first multiply A1 and A2 in the first group and take its map, then they coincide. Okay. So if the map F satisfies this, then we say F is a group homomorphism. Okay, is this clear what I mean?
Could you repeat the part again?
Yeah, so suppose that we have, let me draw a picture. Okay, suppose we have a group, say A, and we have two elements, say any element, say A1 and A2. So when we multiply A1 and A2, we will come to some other elements, say A3, right? Now suppose that there's another group, say B, in a way such that A1 gets mapped to some element here, say F of A1. And A2 gets mapped to some other element, F of A2. Now in the first group, A3 is A1 times A2, right? Now here, there's going to be some element such that this element is going to be F of A1 times F of A2. F of A1, F of A2, okay? Now, if I apply the map on A3, if that map brings me here, then that group element, then that map is called a group homomorphism. Okay, so again, if A1 and A2 are elements of A, and we multiply them, we get to some other elements, say, say A3, then if I apply the map individually to A1 and A2, I get to say B1 and B2, and that B1 and B2, when I multiply them, should be the same as if I apply F on A1 times A2, that should give me B3. Okay, so this is
it like
fact,
the map's name is group holomorphism, or the two groups are homomorphic to each other? Like, what's the group homomorphism point to?
The thing is, a homomorphism is a map, right? A group homomorphism is a map that preserves the group structure, the group multiplication. Okay, so the idea is that a group, homomorphism is a map that preserves the group structure. So this is kind of, this is actually not very difficult. Maybe I made it a bit more convoluted. So I actually think that this definition itself should be enough to kind of, if you mull over it, should be enough for you to understand what a group homomorphism is. So it's a map. So the thing is that, there are two groups, right? A and B. And they have different multiplications, right? They're different sets in general. And there are different multiplications in general, right? So if I take two elements in A, say A1 and A2, and if I multiply them together, and the map takes me to some element in B, right? Now, if I had taken each of these elements, A1 and A2, separately to this new group, B, this new set, there is no guarantee in general that when I multiply these two elements in B, that they will take me to the same element as the right-hand side. If it does, that means that, the multiplication structure we see in the argument of this map is preserved under the mapping. And that's why we call it a group homomorphism, okay? Otherwise, it would just be a homomorphism. If this was not the case, that would just be a homomorphism. Okay, so the important comment is that the group homomorphism is a map that preserves the group structure. When we say group structure, I mean the group multiplication. So group structure is often used to, basically the group multiplication table is preserved. Okay, so the group multiplication. That's what I mean by group structure, okay? So comment number 2 is that, and we shall see examples of this, group homomorphisms don't have to be one-to-one, okay? So you can have, say, two groups, and you can have group homomorphisms where, two guys map to the same thing, A and B, okay? So group homomorphisms don't have to be one-to-one. In fact, there are very interesting examples of group homomorphism which are not one-to-one, which have a lot of application in quantum physics. For example, the rotation group in quantum physics. Number 3 is that, the group homomorphism will always map EA to EB, okay? And that follows from the fact that it preserves the structure. Okay, so we have a few more minutes. I have some homeworks for you to chew on, but I will not homeworks like class exercises, but I will give them related to group homomorphism. Do you want them now, or do you want them after I cover the other group?
Now, sir.
Okay, so yeah, these are actually kind of, they're not hard, but they are not easy either, okay? So show that the image of the group homomorphism F is a subgroup of B, okay? So if this is my group A and this is my group B, and suppose that the group homomorphism is such that it's not onto, it doesn't map you to all of B, it just maps you to a subset of B, okay? So A is all purple, and this all purple maps to the purple subset of B, and this is F. So this is F, and so this purple region is the image of F. Okay, this is called the image of the map F. Okay, so so you have to show that this image of F is itself a subgroup of B. Okay, I'm going to define image for you, and then we're going to go on a break. Okay, so what is an image? The image, the definition of the image of F is all those elements, all those elements in B such that B is in the image of the map for A, for all A in the first group. Okay, so that's the definition of an image. Okay, so it's 6 o'clock, so let us take a break and meet back here at 6:15. Okay. Is that all right?
Yes.
Okay, we have some messages. So Saif is saying, is the geometric interpretation of conjugacy classes, does alpha have to be a rotation for the interpretation to hold? Since B need not be a reflection necessarily. And Nahi has answered, I think so, as alpha is a rotation in the first place, otherwise the construction of the group doesn't make sense. So, I mean, I think, I like Nahi's answer, but I will also say that this is a very general structure. So although I gave you, because I introduced the dihedral group as a group of rotation of an object, so there, like rotation and reflections are natural operations. But there are other groups which may not have such a geometric interpretation. And in those groups, you will also have conjugacy classes. And when you have conjugacy classes, they will have some other notion of equivalence that you will have to figure out in that context, okay? All right, is that okay?
Yeah, makes sense.
So, so this is the first assignment, or not assignment, but the exercise I want you to do. But the second exercise I want you to do is the following about group homomorphism, and show that the kernel of the map F is a normal subgroup of A. So what do you mean by that? Again, let's draw some pictures. So say this is A, and say this is B. So what is the kernel? The kernel is the subset of A that maps to the identity element in B. So suppose that we have all these elements in B, sorry, and make them purple. And in A, all these elements in A, and there is one element in B, which is, say, the identity element of EB. And the map is such that all these elements, purple in A, map to the identity element in B. Then what you have to show is that this subset of A which is the kernel of the map F, it's a normal subgroup of A. Okay, so this is yours. Other exercise second exercise about group homomorphisms. Okay, so let me define what a kernel is. So the kernel of a map, okay, definition, is the kernel of the map F are all elements in A such that the map of A takes you to E of B. Okay? So these are straightforward exercises, and but very, very instructive. And I can do them in class, but I think having to do them at some point after you have done them all, you have tried to do them. I will go over it in class, but it's very instructive for you to try to do them yourself. Okay. So the whole point of this, in-class exercise is it doesn't carry grade, but it's for you to learn the subject. If you don't do these exercises, you're not going to be able to learn. Learning something is not about just absorbing information. Learning something is about making new connections in your brain. And trying to prove these theorems will help you kind of, make new connections in your brain, okay? Okay, do you have any questions?